to dreams. Tonight, we're taking a calm, quiet journey to one of the strangest destinations in all of space, the heart of a collapsed star. These are the leftovers of brilliant giants, stars that lived gloriously, died dramatically, left behind something so dense, so bizarre, so quietly powerful that even time and space bend politely around them. Neutron stars, tiny, heavy, mysterious things that defy intuition and ignite wonder. So, wherever you are, maybe you're tucked under warm blankets, curled up on a couch, or floating in that pre-sleep space between thoughts. I hope this helps you ease into a restful state. If it doesn't lull you straight to sleep, well, at least you'll pick up some astrophysics along the way. I suppose that's the risk of making relaxing videos that are almost too interesting. If you're enjoying the journey already, I'd be ever so grateful if you gave this video a gentle like and perhaps subscribed so you don't miss the next cosmic bedtime story. I'd also love to know where in the world you're watching from and what time it is in your corner of the cosmos. Drop it in the comments if you're still awake by the end. Now breathe slowly, get comfortable. The stars have exploded, but all is calm. This video is for educational and relaxation purposes only. It is not intended as medical advice, diagnosis, or treatment. Please consult a professional for any health-related concerns, including excessive fascination with neutron stars. Long before a neutron star is born, before the collapse, before the cataclysm, before the crushing density, there is a cloud, a quiet, sprawling nursery made not of brick or stone, but of gas, dust, and the leftovers of other long-dead stars. These are stellar nurseries, and if you zoom out far enough they look like delicate wisps floating in the darkness. But inside, they're anything but still. Gravity is busy, very, very busy. A star begins not with a bang, but with a sag. Over time, particles in a molecular cloud begin to gather, drawn to each other by gravity's invisible pull. Imagine grains of sand rolling together slowly on a trampoline. More mass means more gravity, which means more attraction, which means even more mass. It's a feedback loop that ends with something glowing. Eventually, a core forms, a knot of matter that's dense enough and hot enough to ignite nuclear fusion. This is the magic that turns a clump of dust into a baby star. Hydrogen atoms smash together to form helium, releasing energy in the process. That energy pushes outward, fighting against gravity's inward pull. The result is a delicate balance, a star suspended between collapse and explosion, glowing gently in the vastness of space. But not all stars are created equal. Some are small and quiet, red dwarfs that simmer for trillions of years without much fuss. Others, like our sun, live moderate lives, about 10 billion years of stable warmth and light. And then there are the giants, these massive stars, the future parents of neutron stars, live fast, burn hot, and die young. They're dramatic, overachieving, and quite frankly, exhausting. To qualify for neutron star parenthood, a star needs to start off with at least 8 times the mass of our Sun. Some of them are dozens of times more massive. These stellar heavyweights go through their fuel like there's a cosmic deadline. They fuse hydrogen into helium, then helium into carbon, then carbon into oxygen, and on, creating heavier and heavier elements in their cores. Each stage burns faster than the last, like a candle flame being fed pure oxygen. Eventually the fusion chain reaches iron, and this is where everything changes. You see, iron is special. Unlike lighter elements, you can't extract energy by fusing iron atoms together. It just doesn't work. In fact, trying to fuse iron costs energy. So when a star builds up a core of iron, it's like reaching the end of a highway with no exits. The engine stalls, fusion stops, and with no outward pressure to counterbalance gravity, the star begins to fall inward on itself. But we'll get to that in another moment. Let's linger just a bit longer on the life of a massive star, because honestly, it deserves some appreciation. These stars are cosmic forges. Almost everything you're made of, the carbon in your DNA, the calcium in your bones, the oxygen you're breathing right now, was born inside a star like this, billions of years ago. Stars don't just light up the universe, they build it, and they do it with flair. Massive stars often end their lives in grand style, forming beautiful bubbles of hot gas, sculpting the interstellar medium, and sometimes forming binary systems with equally dramatic partners. They can spin rapidly, throw off enormous stellar winds, and even pulse in brightness as their internal dynamics shift and evolve. They're not so different from teenagers, really. Brilliant, unpredictable, and destined to change. But what makes one of these massive stars destined to become a neutron star instead of, say, a black hole? The answer lies in the delicate balance between mass and resistance. When the core collapses, it does so with astonishing speed, a fraction of a second faster than you can blink. Temperatures skyrocket to hundreds of billions of degrees. The outer layers of the star crash inward, slamming into the core, then rebounding outward in a powerful shock wave. This explosion is what we call a supernova, one of the most energetic events in the universe. It can briefly outshine an entire galaxy. If the collapsing core is not quite massive enough to become a black hole, but too massive to remain a white dwarf, it finds a strange middle ground. The pressure from all those neutrons packed together halts the collapse, at least temporarily, and what's left is a neutron star, a remnant about the size of a city, yet more massive than our Sun. But we're getting ahead of ourselves. For now, just remember this. Stars are the great recyclers of the universe. They take simple ingredients, hydrogen, helium, and turn them into the stuff of planets, oceans, flowers, and people. They spend their lives quietly resisting gravity, only to be undone by it in the end. And in their final moments, they light up the universe with a brilliance that echoes across space and time. It's peaceful in a way, poetic. A star collapses and something new is born. Not quite alive, not quite dead, just different, quiet, dense, mysterious. So the next time you look up at the night sky, remember that some of those twinkling points are the calm survivors of ancient chaos. They've seen their suns die, their cores implode, and now they spin in silence, holding secrets heavier than anything on earth. All of that from a simple cloud of dust. A star spends most of its life in a careful balancing act, performing an elegant fusion-powered dance that keeps it from collapsing under its own immense weight. But nothing lasts forever, not even in space. Eventually, for the universe's most massive stars, that delicate harmony unravels in a matter of seconds, and when it does, something truly spectacular happens. The star explodes. Tonight, we're easing into that dramatic finale, the supernova. Don't worry, we'll take it slow. For billions of years, a massive star burns like a furnace, converting lighter elements into heavier ones in a process known as nuclear fusion. It starts with hydrogen, the simplest and most abundant element in the universe. The star fuses hydrogen atoms into helium, releasing energy in the process. This energy pushes outward, keeping the star puffed up like a balloon against the relentless inward pull of gravity. But hydrogen doesn't last forever. When it runs low in the core, the star begins to fuse helium into carbon, then carbon into oxygen, then oxygen into neon, neon into magnesium, magnesium into silicon, and finally silicon into iron. Each step up the periodic table happens faster and faster. In the star's final days, these fusion processes might only last a few years, months, or even just days. And then it hits the iron wall. Iron is special in a frustrating kind of way. Unlike the lighter elements, you can't extract energy by fusing iron atoms together. Instead of releasing energy, fusing iron consumes it. It's like trying to power a light bulb by stuffing it with used batteries. Nothing happens, and everything just gets hotter and more unstable. Once the core of the star fills with iron, the fusion engine effectively shuts down. Gravity, which has been held in check for millions of years, suddenly has nothing to push back against. The balance breaks, and when that happens, the star begins to fall in on itself. Now this is where things speed up dramatically. In less than a second, the core begins to collapse. Temperatures soar to over 100 billion degrees. The pressure becomes so intense that electrons are forced into protons, creating neutrons and neutrinos. This process is called electron capture. It turns the core into a soup of densely packed neutrons, while a flood of neutrinos, nearly massless ghostly particles, escape in all directions. Imagine a bowling ball collapsing into a marble in the blink of an eye. That's the kind of scale we're talking about here. The core, once thousands of kilometers across, compresses into a dense sphere only about 20 kilometers wide. And in that same instant, the outer layers of the star, no longer supported by fusion, crash inward at a significant fraction of the speed of light. But this inward collapse doesn't go on forever. When the falling material hits the incompressible core of neutrons, it rebounds. It's like trying to crush a diamond with a pillow. The outer layers slam into an unyielding wall. This rebound, combined with the outward rush of neutrinos, creates a shock wave, and that shock wave punches through the collapsing star, blasting the outer layers into space in a cosmic detonation known as a supernova. A supernova is, frankly, absurd. For a brief period, a single exploding star can outshine an entire galaxy made up of hundreds of billions of stars. The energy released in a few seconds is more than our sun will emit in its entire lifetime. If that sounds excessive, well, stars do love a grand exit. To an outside observer, this explosion looks like a sudden brightening in the sky, followed by a slow fade over weeks or months. But inside the star, it's chaos. Shock waves rip through the outer layers. The star's material is torn apart, scattered across light years. Elements forged in the star's core, carbon, oxygen, calcium, even iron, are flung into the cosmos. These elements will go on to form new stars, planets, and maybe even life. In fact, every atom of iron in your blood came from a supernova. Every bit of calcium in your teeth, every speck of oxygen in your lungs. That's the poetic part of stellar death. It's also cosmic recycling. The end of one star becomes the beginning of countless other things. But not all of the star is destroyed. At the heart of the explosion, something remains. If the original star was massive enough, at least 8 times the mass of our sun, the collapsed core will survive the blast, and depending on its exact mass, it will either become a neutron star or, if even more massive, collapse further into a black hole. But we'll save that darker path for another day. Let's linger with the neutron star. Right after the supernova, this newborn neutron star is incredibly hot, over 100 billion degrees, but it cools quickly, radiating away energy through neutrinos and light. It spins rapidly, often several times per second, and its magnetic field intensifies to unimaginable levels. In just a moment, the gentle fusion-powered glow of a living star is replaced with a dense, spinning magnetic corpse, packed tighter than anything else in the universe short of a black hole. From the outside, it's hard to grasp just how violent this process is. But if you were a neutrino, born in the heart of that collapsing core, you'd be ejected at nearly the speed of light. you'd pass effortlessly through the rest of the star, through the explosion, and keep going, through planets, moons, people, because neutrinos rarely interact with anything at all. And yet trillions of them pass through your body every second. That's not an exaggeration. It's a gentle, invisible truth of everyday life. The explosion also sends ripples through space-time itself. These are gravitational waves, subtle distortions in the fabric of the universe, radiating out from the dying star. We've only just begun to detect them in recent years, but they tell us stories that light alone cannot. Supernovae are rare in our galaxy, perhaps only one every 100 years, but their light can be seen across vast distances. Some of the most famous historical records of guest stars in the night sky were actually supernovae. Ancient astronomers from China, Japan, and the Middle East recorded bright new stars appearing for days or weeks before fading away. In one case, a supernova observed in the year 1054 left behind the Crab Nebula, still visible today through a telescope, and at its center a pulsar, a spinning neutron star left behind by the explosion. From the calm to the catastrophic, the life of a massive star is a slow burn followed by an astonishing finale. For millions of years it held itself together, fusing elements and glowing steadily, and then, in its final moments, it collapses, explodes, and scatters its essence across the universe. It's strange, really, that such violence can lead to such beauty, that something so devastating can be the source of new beginnings. But the universe is full of these contradictions, explosions that create, deaths that give life, stillness born from fury, and at the center of it all a small, dense remnant, quiet now, but full of secrets. When a massive star dies in a supernova, most of its outer layers are thrown violently into space, becoming part of the galactic tapestry. Drifting gas clouds, raw material for new stars, maybe even the building blocks of future planets. But the core does something very strange. It collapses, yes, but then it stops collapsing. Not into a black hole, not quite. It lands in an in-between state, a bizarre state, and what's left behind is one of the universe's most extreme objects, a neutron star. So, what exactly happens in those chaotic final moments when a star folds in on itself? Let's imagine we could pause the universe just as the supernova is about to detonate. Let's zoom in, not on the explosion, but on the core, and what's happening at the smallest scale. The core of the star has become an iron ball, incredibly dense and under tremendous pressure. Iron, as we now know, can't be fused into heavier elements without consuming more energy than it gives off. So fusion stops. With nothing pushing outward, gravity takes over, and it does not take its time. In less than a second, gravity crushes the core inward. Atoms are smashed together so forcefully that the electrons, which normally whirl around the nucleus like excited children on a playground, are forced into the protons at the center. This combination turns protons and electrons into neutrons, electrically neutral particles with no charge and very little personal space. This process is called neutronization, and it fills the collapsing core with, well, neutrons. Lots and lots of neutrons. It's like the entire core becomes one giant atomic nucleus, with the protons and electrons wiped away, leaving behind an ocean of pure neutron matter. The neutrinos, ghost-like particles created in this process, burst out, carrying away huge amounts of energy. For a moment, this core is more dense than anything in the visible universe, hotter than the center of a nuclear explosion, and somehow still not a black hole. The reason it stops collapsing, at least for now, is because of a strange kind of pressure. Not the kind you feel when you've got a deadline coming up. No, this is quantum pressure. More specifically, neutron degeneracy pressure. It's a consequence of the Pauli exclusion principle, a rule from quantum mechanics that says no two identical particles can occupy the same quantum state. In other words, neutrons don't like to be crowded. They push back, and that push is enough to stop gravity, unless there's too much mass, in which case, hello black hole. But if the mass is just right, somewhere between about 1.4 and 2.3 times the mass of our Sun, this neutron degeneracy pressure is enough to hold up the star's weight. And so the collapse halts, the core stabilizes, the explosion continues outward, but at the center something new has formed, a neutron star. Now let's pause and appreciate just how weird this object is. A neutron star packs more than the mass of the Sun into a sphere only about 20 kilometers wide. That's roughly the size of a small city. You could walk across it in a few hours if, of course, you could avoid being crushed, vaporized, or turned into subatomic mist. To put it another way, imagine taking a jumbo jet and compressing it down to the size of a sugar cube. That's the kind of density we're talking about. 1 cubic centimeter, about the size of a dice, would weigh as much as Mount Everest. And yet, this whole thing is sitting quietly in space, spinning, cooling, and occasionally flashing its magnetic beams like a celestial lighthouse. Inside the neutron star, things get even stranger. The outermost layer is called the atmosphere, though it's nothing like the air we breathe. It's a paper-thin layer of exotic plasma, where light and matter blur together in strange high-energy interactions. Beneath that is the crust. But don't let the word crust fool you. This is not a gentle outer shell. It's a layer of ultra-dense, super-rigid nuclear matter. At the top of the crust you find nuclei packed tightly together, surrounded by a sea of electrons. As you go deeper, the pressure increases, forcing the nuclei into increasingly bizarre shapes. Scientists call these nuclear pasta. Yes, really, because of their resemblance to spaghetti, lasagna, and other pasta-like forms. These structures are the result of nuclear forces battling gravity in a cosmic tug of war, and they're probably the strongest material in the universe. Below the crust is the core, and here things get speculative. We believe the outer core is a superfluid of neutrons, meaning the neutrons flow without friction. Imagine a liquid that never slows down, that doesn't splash, that behaves like it's from a sci-fi novel. That's the state of matter in the core of a neutron star. Go deeper still, and things become even more uncertain. Some theories suggest that the pressure might break down the neutrons into their constituent quarks, creating a soup of quark matter, a kind of ultra-exotic state that might exist nowhere else in the universe. Others believe the core might contain hyperons, strange particles with names that sound like comic book villains. The truth is, we don't know for sure. No laboratory on Earth can replicate these conditions. All we can do is observe, calculate, and wonder. One thing we do know, neutron stars spin, and they spin fast. The conservation of angular momentum, a fancy way of saying what spins keeps spinning, means that as the star collapses it spins faster and faster. Think of a figure skater pulling in their arms during a spin. A massive star that once rotated once every few days might, as a neutron star, rotate dozens or even hundreds of times per second. These spinning neutron stars are called pulsars, and they emit beams of electromagnetic radiation from their magnetic poles. If those beams sweep past Earth, we see them as regular pulses, like a lighthouse beam in the night. Neutron stars also have magnetic fields, colossal ones. When the star collapses, its magnetic field intensifies, like squeezing a magnet tighter and tighter. Some neutron stars, known as magnetars, have magnetic fields over a quadrillion times stronger than Earth's. That's a 1 followed by 15 zeros. It's so strong that it could strip the information from a credit card from a distance halfway to the moon. Fortunately, magnetars tend to mind their own business and stay far, far away. All of this, the insane density, the crushing gravity, the exotic matter, the magnetic fury, is packed into a sphere the size of a city, hanging quietly in the cosmos. It's easy to forget that these bizarre objects started life as ordinary stars, fusing hydrogen in their cores, glowing softly, drifting along with their galactic neighbours, and now they sit as remnants, as relics, as testaments to the violence and wonder of stellar death. Neutron stars are strange, but they are also beautiful. They are compact records of physics at the edge, full of secrets we're only beginning to understand. They are the middle children of stellar evolution, not quite stars, not quite black holes, but with their own fascinating personality. And while they may seem distant, even alien, they are part of the same story we are. The iron in our blood, the calcium in our bones, all forged in the same fiery deaths that give birth to neutron stars. We are in a very real way, made from the same stardust. And maybe, just maybe, that's why we find them so mesmerizing. A neutron star is small, just about 20 kilometers across. That's roughly the length of a leisurely morning drive through the countryside. But what it lacks in size, it more than makes up for in density. This is not just a heavy object. This is the heavyweight champion of the universe, short of black holes. It's a place where matter has been crushed so tightly that atoms no longer resemble anything we've ever seen on Earth. If the laws of physics had a basement, neutron stars would live in it. Let's start with the basics. Imagine scooping up a teaspoon of neutron star matter. Not a big ladle, just a gentle, dainty teaspoon. That single spoonful would weigh about 6 billion tons. That's roughly the mass of Mount Everest, crammed into something small enough to stir your tea with. Only, of course, you couldn't stir this matter. You couldn't even get close to it. It would drop straight through the planet, slicing clean through the mantle, core, and whatever else got in its way before exiting out the other side. Then it would probably continue falling through space, radiating menace and gravity in equal measure. But what is neutron star matter exactly? What happens to ordinary stuff, protons, electrons, atoms, molecules, when gravity goes completely overboard? Let's peel back the layers. Starting at the surface, we find a layer so thin it barely exists, the atmosphere. It's only a few centimeters thick and consists of plasma, a mix of electrons and nuclei, whipped into a frenzy by incredible gravity and magnetic fields. This air isn't the kind you'd want to breathe. It's hot, dense, and crackling with radiation. Light behaves oddly here. Because the gravitational field is so intense, photons trying to escape the star are redshifted, stretched into longer wavelengths, before they finally break free. Even colour takes a beating in this environment. Beneath the atmosphere is the outer crust. Now, crust might sound comforting, perhaps even edible. But this is no golden pastry. The outer crust of a neutron star is a layer of ultra-dense crystalline nuclei packed together like sardines in a sardine can. Only the can has been stomped on by an entire planet. These nuclei are surrounded by a sea of free electrons. The gravity is so strong here that if you dropped a marble from waist height, it would hit the surface at several thousand kilometers per second. That's fast enough to vaporize the marble, and quite possibly your waist too. Deeper still is the inner crust. Here the pressure is so great that electrons start merging with protons inside nuclei, turning them into neutrons. These neutrons begin to drip out, forming a sort of neutron-rich soup that coexist with nuclear clusters. It's a strange halfway place, part solid, part liquid, part question mark. Scientists call this the neutron drip region, and it's exactly as surreal as it sounds. And then we come to one of the weirdest parts of the neutron star, the pasta layer. No, this isn't a joke. Physicists, after working with brutally complex nuclear models for years, finally said, "Fine, it looks like spaghetti. Let's just call it that." And so they did. In this region, between the crust and the core, atomic nuclei arrange themselves into long rods, flat sheets, and blobs. Depending on the shape, they've been nicknamed spaghetti, lasagna, gnocchi, and even Swiss cheese. This isn't culinary whimsy. These structures emerge from the fierce competition between the strong nuclear force and gravity. The result is nuclear matter that's denser than anything on Earth and organized into some of the strangest shapes in the universe. And here's the wildest part. This pasta layer might be the strongest material known to science, over 10 billion times stronger than steel. If you somehow managed to forge a bridge out of neutron star pasta, it would withstand practically anything short of a black hole's hug. Moving inward, we reach the outer core. This is where things go from weird to our best guess. The density here is higher than anything you can create in a lab, so physicists rely on models, math, and the occasional prayer. Most agree that the outer core is made of a superfluid, a state of matter where neutrons move without resistance. Imagine a liquid that flows forever, never slowing down, never settling, and never clumping. A fluid so smooth that if you stirred it, it would spin in perfect silence forever. This superfluid neutron soup might also contain protons and electrons, although the protons would be in a superconducting state, allowing electric current to flow without resistance. These particles interact in ways